Thank you for having me. I've been invited to talk about perspectives. It's a little high-flying, I think. I'm going to change that directly into illustrations. I'm going to show a little bit what we do, just to showcase what's happening in this field. So quickly, I'm a business developer at RISE, and see if I can advance this. So RISE is a Swedish institute. We are roughly 2,800 people with around 130 different test beds. And then, of course, the printed electronics arena is one of them. This is an innovation cluster based in Norrköping. And for those who are not aware where this is, it's very close to the North Pole. So we're up here 1 hour south of Stockholm. And summertime, like now in June, you might even surf in the middle of town if you happen to have a surfboard, which is electric, of course. Now, the innovation cluster is actually a combination of academic research at the University of Linköping, where you have around 150 postdocs, PhDs in chemistry doing work in organic electronics, and downstream you have all kinds of clients. We tend to clients from everywhere in the world. They can be small inventors and also multinationals. And our position is to be in the middle, bridging the gap between academy and industry. Looking at the academic side, there's chemistry labs, scientists working into taming the ionic properties of conducting polymers into plants, also research into cellulose. In this case, you have cellulose, a non-fibrillated cellulose, which is doped with conducting polymer, and all of a sudden you have a black paper that can store electricity. Quickly zooming out again, the RFID labels are printed, and they are made in the 20 billions globally a year. The glucose strip test to the left, where you leave a little drop of blood to test your blood sugar level, also made in the billions. But the interesting thing is that they're actually made by means of screen printing. Now, at the PIA, we are working with all these dimensions, both the chemical side of things, but also the manufacturing, prototyping. And we mostly work with screen printing and inkjetting. We have a whole bunch of different machines to help us. And then we are typically working with prototyping, early stage prototyping, rather than series manufacturing. So it might look like this on an ordinary day, where we combine flexible materials, conducting polymers, and also then conventional electronics into different types of systems to address whatever need the client has. So here's an example where we're actually mounting hard electronics onto textile, which will then form a sock. I'll show you an image in a second. Here's an example of how we're trying out the cycling of PDOT or conducting polymers with different temperature settings. And one of the key things for us is that we are totally technology agnostic. We are independent. We use whatever is needed, whatever technology is available on the market to help the clients. One field, one example are piezo-sensitive polymers. You can see the gray dots here. They are printed, screen printed sensors mounted onto a sole of a horse or under the horseshoe. And then this little system might be used to detect if the horse is having a problem walking, trotting, if there's a lilt, if there's some kind of injury to the horse. Another field which is moving quite fast is different types of substrates and inks that are stretchable, which will allow for new types of form factors and new types of systems that might be used in conjunction with the human body, in the body, on the body. Potentially also biocompatible. And to the right, you see the sock I mentioned just a second ago. It's a sock that might be used to detect leg swelling, which is coupled to edema and maybe heart problems. So potentially the sensor might respond to leg swelling and then also address medication in case you're about to have a heart attack because for various reasons you have a poor heart, you've had cancer surgery, etc. The little ion pump is an electrophoretic device which might be implantable to very specifically deliver drugs to specific areas in the body. And in combination, you can take all these sensors, put them on the body, inside the body, and create networks. And we are flying high, we're aiming very, very high. In this case, we're looking at treating epilepsy, or ideally detecting some kind of marker before the seizure happens. So another field, passive sensors. In this case, it's a passive humidity sensor, which might be used to install inside houses, and you have a little scanner that can detect this little radio antenna and then see if the sensor has been exposed to humidity or not, and thus you can tell if the house, if there's a risk for mold build, for instance. The same type of technology, looking for humidity in a bandage. You don't want to change a bandage too early and not too late. And there's a combination of a passive printed humidity sensor and an electrochromic display, very much like the ones we are using together with Ynvisible, and passive system to say that the bandage needs to be changed. Now, moving towards the field where we're collaborating with Ynvisible is electrochromism, of course. We have a little patent portfolio around the inks and formulations and also the different buildups. And as you may know, electrochromism means literally that you change the chroma with the electro, you change in color with electric current. And that is used, for instance, in some of the aircraft windows and also in rear view mirrors in cars. So this is a very important field for us. Looking at the little displays, they are low power, possible to produce in roll to roll and then upscaling. For instance, together with Ynvisible, which is a great partner for us. We also do this manually, very, very manual trials, but we can also go into automated production. And we try every dimension of these displays and testing and also miniaturization. In this case, you have a little printed transistors. There's actually a world record there. And looking here, we have a copper print, very, very high resolution copper print. You can see down right, it says 100 micrometers. So it's very, very high resolution printing we're talking about. And with a few transistors, if you look at any kind of smartphone, you'll have several billion, even 400 billion transistors in all your memories, but this is like 120. So with some perspective, this is not a lot of transistors, but that might be sufficient to drive a few segments of a display. And there's no need for actual integrated circuits based on silicon. These transistors also can act as sensors. So organic electrochemical transistors can both amplify a chemical signal and also detect something, some kind of marker. And they can take different forms. And in this, just as an example, it's been trialed to use as a lactate biosensor. So combining these technologies, we can create little systems, or small or big as you please. And mounting conventional chips on top of this, we may add computational power into smart systems that can detect things. Here's one example, which is a temperature logger. You have a conventional chip from NXP, which can then store roughly 8,000 data points. And in this case, we're addressing the cold chain for vaccine monitoring. Several consecutive R&D projects together with the Doctors Without Borders and financed by the Swedish Innovation Agency. So this little label is a very smart logger in a very small form with an onboard display to indicate if the vaccine has gone bad or is still good. Another example here would be a bit more futuristic, a platform that's looking for drugs of abuse in saliva. It's actually based on nanocellulose substrate. Very, very futuristic, but a beautiful concept. Now, we're also playing around a little bit with color on the displays. We're having a steep learning curve right now. Still dabbling a bit, trying to master the color systems, trying things to see if we can achieve color combination and form combinations in a way that we can, well, again, expand the use for electrochromic displays, really. So final picture, one other example, one field is also how to make these displays smarter, more operational, potentially substituting LCDs. So electronic shelf labels or liquid crystal displays of all kinds might in the future be completely substituted by this technology if we can keep in this direction. So that's all I wanted to say. Thank you so much.